بسم الله الرحمن الرحيم. Welcome to Tahar Scholar. We are الثلاثاء 19 ديسمبر 23 بالجزائر, or in English Tuesday 19th December 23 in Algeria. We are still in our series Programming with Matlab, and this is practical number 7, and it's the last practical in this series. We have started in the last practical, in the previous practical number 6, a series of 3 exercises. We have solved exercise number 1 and exercise number 2, and now we are in the exercise number 3, which is about Elkarkhi's triangle and binomials. If you have not already read the series, please check it in the previous practical. So here I have drawn the triangle of Elkarkhi with the order n equal 4. So let us study the pattern. First thing to observe is that the number of rows in the triangle is equal to the order of the triangle plus 1. And second thing, so let's write it here, the number of rows is equal to the order n plus 1. To the order n plus 1. The second point here, so let's write here algorithm. The first point is the algorithm. We try to write an algorithm to generate the triangle. We first study the pattern. So the second point is the number of elements in each row. As you can see, the number of elements is equal to the index of the row. It's the second row, we have 2 elements. I equal 3, we have 3 elements. I equal 4, we have 4 elements, and so on. So at the ith row, there are I elements. The second thing to observe here is that each row starts with 1 and ends with 1. Always. So each row starts with 1 and ends with 1. Now, what about the inner elements that I have here written in red? What about the inner elements? So let's check first. The inner elements start from the third row. The first and the second row have no inner elements. So 2 is 1 plus 1. 1 plus 1 equal 2. And in the fourth row, we use the third row. To generate the fourth row, we use the previous row. So 1 plus 2 is 3. 2 plus 1 is 3. Same for the fifth row. We use the previous row to generate the inner elements. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and so on. So you take the column, for example, I want to calculate this element. This element is at I equal 5, and the third column, this is the third column. What we do, I go to the previous row, the same column, the third column, and the previous column, and I add them. I add them to generate the element I want. So at the jth column, in the ith row, I take the elements in the previous row, but at the jth column and j minus 1. And that's it. So let's write the algorithm. It's very simple. First thing first, where we store our row. We cannot store it in a matrix because each row has a different size. So we use a cell array. So the first thing to do is to store our triangle, in a cell array. And let's call it U. So U, the cell array U, it is a vector, and each element of it is a cell. So we use the function cell. We use the function cell, n plus 1 elements. It has n plus 1 elements. Each element is a row and one column. It is a column vector. We could also use a row vector. It's the same. We can also use cell 1 n plus 1. They are the same, are equivalent. So this is the first thing to do. Then we use a loop to cross each row. So we use a loop I from 1 till n plus 1. And in this loop, we first set the contents of the cell. Each cell contains a row vector of integers. So the contents of the cell at the ith row is, let's initialize it, all the elements with 1. Because they start with 1 and 1, we initialize it, like for example, I3, we initialize it with 1, 1, 1. What is this? This is ones, the function ones, 1 row and 3 elements. If I here is 3. So we use the function ones to initialize the contents at each index. So we use ones, 1i. So we use I because the size of the row is equal to the index, as we have seen in the pattern. At the ith row, there are I elements at the ith row. And we use braces because we want to initialize the content of the cell. And then comes the inner elements. So the inner elements starts from the second element in the row till the element just before the last. So they start from 2 till I minus 1. So we have 2 loops. This is the inner loop and this is the outer loop. In the inner loop, we set the inner elements. So what we have said before, that any element in the current row is set using the elements from the previous row. So we use the cell at the ith row, at the column J, let's write it here like this. At the column J, we take two elements from the previous row. So this is row I minus 1, and this is row I. But the elements are not random, of course. They must be at the jth column and j minus 1. and we just add them to get the element in this cell, in this box, ij. So the ij element is equal from the previous row, I minus 1, the element at the jth column, plus u I minus 1. Both are at the row I minus 1 and j minus 1. So just an addition of two elements that are located just in the previous row, at the jth and j minus 1. That's exactly what we have done. Now be careful here, braces for the row and parentheses for the element, because this is a row vector. This is a row vector. That's why we use parentheses. This is also a row vector, the same row vector. And the element, we access the element in a vector always using parentheses, as usual. And that's it. This is our algorithm. We have two loops. We have first to store our array, and then we cross each row of the triangle using the index I, and then we set the row first using the function ones. Ones will generate a row vector containing I elements, I integers, and then we set the inner elements using the pattern that I have showed here. So the element at the jth column depends of the elements in the previous row at the jth column and j minus 1. We just add them. It's just an addition. So let us make before to go to the programming set to the computer setting. Let us test the algorithm. So first algorithm, the second testing our algorithm. Testing the algorithm. So for I equal 1, we generate a vector of one element containing 1, because we use function ones. So this is for I equal 1. And we do not loop here, because the loop will be from 2 to 0. So here the loop j will go from 2 to 0. There is no sequence from 2 to this. It's empty. It's an empty sequence. So the loop will never be executed. Will be skipped. Then we do I equal 2. For I equal 2, we set first the cell using ones, 2 elements. So 2 elements, a row of 2 elements, and all the elements are equals to 1 because we use function ones. And then for j equal 2 to 1. It's also an empty sequence. An empty sequence. So this loop will not be executed. This loop will not be executed for I equal 1 and I equal 2 because there are no in this two first row, there are no inner elements. That's why the loop will not be the loop j will not be executed. And then we continue our loop I equal 3. The function ones will generate a row vector of 3 elements. All the elements are equal to 1. So here we have 1, and here we have 1 also. And then we go to j. J will go from 2 to 2. J will go from 2 to 2. Means j equal to, there is only, the sequence has only one element. So for j equal to, what we have? For j equal to, we go to the previous row. That's what tell me here the equation. We go for I equal -1. So I -1 is the second row. And we go to the jth and j -1 column. So we go here and here, and we add them. We get 2. So n will be erased, and the new value will be set. And we have 1 to 1, like here in the figure, 1 to 1. And then, so this is for the loop here. And then I equal 4. For I equal 4, the function ones will generate a vector of 4 elements, a row vector, 4 elements, and all the elements are equals to 1. This is what ones do. And it assigns it to the ith cell, and then we go to the loop j, the inner loop. So here j starts from 2, I -1, that is 3. So j equal 2 and j equal 3. That's the inner elements. Let's start with j equal 2. So for j equal 2, we take the previous row, this element at the second position, and j -1 at this position. And we add them. We get 3. That's the equation here. I -1 is I equal 3. Is the third row. And j and j -1 are the two, are the second and the first element. Because here j equal 2. For j equal 3, we get the third and the second. So we get these two. For the j equal 2, we have that. And for j equal 3, we have that. So we add 2 plus 1, and we put it here. It becomes also 3. So now we have 1, 3, 3, 1, exactly as in the figure. And we continue, I equal 5, I equal 6, and so on. So I think it's enough to show that the algorithm works correctly. The algorithm works correctly. Let us now go to the computer setting and implement our algorithm. So this is our function, genElkarkhi triangle, Elkarkhi's triangle. It takes as input the order of the triangle, and it returns a cell array containing the triangle. I called it U. So let's read the comment. Generate Elkarkhi's triangle, first version. We will see a second version later. Tahar Scholar, programming with Matlab, practical 7, algorithms. So this is the second part of algorithms by Tahar Jawad, the date and Algeria. The first line tests that or checks that n is an integer. So the integer part is equal to the number itself, and it is positive. And then as we have seen in the notebook setting, we set the cell array using the function cell with n plus 1. Always the number of rows in the triangle is equal to the order plus 1. And it is a column vector or row vector, it doesn't matter. The number of elements must be n plus 1. Then we cross I from 1 till the number of elements in the cell. The first thing to do is to set the contents of the cell, ui, using the function once. And we use here a row vector containing the number of elements equal to the index I, as I explained in the notebook setting. And then the inner loop from j equals 2 to I minus 1. And as I said, we set the element at the column j using the elements in the previous row, but that are located at the jth column and j minus 1. We just add them. And that's it. It's a very simple algorithm. There is 2 loops, the inner and the outer loop. Let's test it. I have already written a script, very simple script. We ask the user to introduce the order of the triangle, and then we call the function with n, and it gets you. Then we display it row by row. So if the number is less than 15, otherwise it become really cumbersome to display it. So for n less than or equal 15, we cross the rows in the cell array, and we display them using num2string. We display the contents. So u braces I. And all the elements are integers with the length 7 characters. So each integer will be displayed in a length of 7. And that's it. And that's it for displaying textually. If n is large, particularly when is large, it's better to display it using the function bar. So we display the last row of the triangle to see the elements visually. So let's execute it. Let's read also the comment. Programming with Matlab, practical 7, algorithms. Generate and display Elkarkhi's triangle of a given order by Tarjouad, 23rd November 2023, Algeria. So, and as usual, of course, we clear all and CLC. So let's execute it. It will ask us to, let's, for example, use the same example we have seen in the notebook and also in the series. So order 4. And as you can see, we have here the same triangle as we have expected. So we have 2 is 1 plus 1. We have here 3, 1 plus 2 equals 3. 2 plus 1 equals 3. 1 plus 3 equals 4. 3 plus 3 equals 6, and so on. And we can see also the figure. So this is the figure. Let's display it a little bit here to be in the screen. Okay. And as you can see here, 1, 2, 3, 4, and 5. This is the last row. And the element here is 1, then 4, and then 6. And you can observe here the symmetry of the elements in the row. Let's do another example. This time, for example, 15. And as you can see, the numbers here, the inner integers in the last rows become very large. Let's see that also in our triangle. And as you can see here, they get 6,000. They are close to 7,000. The amount here is very large than in the beginning and in the end of the row. And also observe the symmetry. Let's do another example, but this time with, let's say, 50. N should not be very large, because otherwise we get number really very big. We cannot store them in memory. We call that overflow. They overflow the integer type. So let's say 50. We cannot display it. It will be very large. It will not fit in the console. So let's see it visually. You can see that here. And as you can see here, if 14 is very large, it's 10 to the power 14. That's 5,000 billion. So it's very large compared to the first elements and the last ones. And that's it for the algorithm. Let's see the performance. Let's go to the notebook setting, see the performance, and continue our exercise. So we have already studied the algorithm and testing it. Now let us study the performance of the algorithm or time complexity. So I have here drawn Elkarkhi's triangle with the order n equals 6. So we have 7 rows, and the main operation is to add 2 integers to get the inner elements. For example, we add 1 plus 1, we get 2, 1 plus 2, we get 3, and so on. What I have drawn here in green. The number of iterations, outer loop, number of iterations in the outer loop, there are 2 loops in our algorithm. The outer loop crosses the rows, and the inner loops crosses the inner elements at each row. So the outer loop starts from 3 till n plus 1. And the inner loops, so the outer loop starts from I equal 3 till n plus 1. So how many iterations we have? We have n plus 1 minus 3 plus 1. The last index minus the first index plus 1 to get the number of iterations in the outer loop, which give us n minus 1 iterations. So we have n minus 1 iterations in the outer loop. And in the inner loop, or inner loops, because there is an inner loop per each iteration. So for I equal 3, we have only 1 iteration. For I equal 4, we have 2. For I equal 5, we have 3, and so on, till the last iteration. So for I equal n plus 1, we have n plus 1 minus 2. We have n plus 1 minus 2, which is n minus 1. What we have drawn here in green, or painted in green. So we have n minus 1 from 1 to, let's write that here, 1 plus 2 plus 3. This is the total number of iterations done by the algorithm. This is for I equal 1, for I equal 3, I mean. And this is for I equal n plus 1. And how many terms? We have n minus 1 iterations, so n minus 1 iterations. And we have seen already that in exercise 1. This is called an arithmetic sequence. An arithmetic sequence. And we know that the sum for an arithmetic sequence is the first term plus the last term by the number of terms over 2, which leads to n by n minus 1 over 2, which is equal to n squared over 2 minus n over 2. And we conclude that the time complexity, so we conclude we have counted how many times we perform the addition. The operation, the main operation is to add two integers from the previous row. So the time complexity is of the order, this term, when n gets sufficiently large, this term is neglected. So we get neglected before this one. So the order is of n squared over 2. Here, be careful or observe that for Elkarkhi's triangle, the inner elements get very, very large, as we have seen on the computer setting when we tested with Octave. Get very, very large. That's why n should not be too large, 50, 60, 70, nothing more. And that's why time complexity is not that big deal. The algorithm is very fast because we have only 50, maybe not exceeding 100 rows. So overall it is very fast, but still it is nice always try to understand how many iterations your algorithm is doing to reach the result. So from this simple study, we can conclude that the time complexity is of the order n squared over 2. And we will see, because of the symmetry, we can reduce that to the half. It can be even twice faster. But for the moment, let us move to the binomials, to use the Elkarkhi's triangle. So the binomial theorem states that whatever x and y in R and whatever n in big N, the set of natural number, except 0 and star means not including 0. We have x plus y to the power of n equals the sum of coefficient ti, index I, x to the power n minus 1, n minus I, and y to the power of I, from I starting to 0, not to 1, till n. That is t0, x, n, plus t1, because y0 is 1, xn minus 1, y, plus t2, xn minus 2, y squared, plus, etc., till tn minus 1, x1, yn minus 1, plus tn. So I ends with n. x0 become 1, so we get yn. And these coefficients are integers, are not real numbers. And they are actually given by Elkarkhi's triangle, by the last line or the last row of Elkarkhi's triangle. So let's write that here. The ti, I from 0 till n, are given by the last row of Elkarkhi's with h. Kha is not in English. So we say KH, Elkarkhi. Elkarkhi's triangle. Okay, what does that mean? That means that Ti, be careful with the index, Ti minus 1 is equal to, we have said that we store the triangle in a cell array. In a cell array. N plus 1, 1. So the cell array, the last row, the contents of the last row is U, N plus 1. We use braces. And here the index is I. So here we use I minus 1, because in Matlab, the index always starts with 1. You cannot use to index a row or a cell array or a structure array by 0. You cannot start by 0. So we do I minus 1. So for the first index, we get T0. So let's write it here. I from 1 till N plus 1. For T0 is UN plus 1, the first element. And T1, which is equal to 1 always. T1 is UN plus 1, 2. And so on. Till the last one, Tn, is UN plus 1, N plus 1. And it is also equal to 1. Because the row starts from 1 and ends from 1, and ends by 1. And this is the theorem of Elkarkhi's triangle. So we have here expanded the index. How he has proved that? He has devised a technique called by induction. When you have an expression that depends on an integer, you prove that it is true for n equal 1. And then you suppose that it is true for n or k, for any given number k. And you prove then that for k plus 1 it is true. You deduce from the fact that it is true from k, you have supposed that it is true from k, you prove then that it is true for k plus 1. This is called mathematical induction. He is the first to do that, the first mathematician to use this reasoning, this logical reasoning. And it is now called mathematical induction. So that's the theorem. Now, how we calculate that? We can use a loop, of course. Very simple. We can use a loop. X and Y are given, n is given, the order of the triangle. We calculate the coefficients using our function, genElkarkhiTriangle, and we replace the value of x and y. But instead of doing a loop, it is better to vectorize that. How we do that? So let's write here. No, let's write here vectorization. So we can observe the following three vectors. The first vector, this is from the sum. We observe xn to the power of n, xn minus 1 in each term, xn minus 2 till x1. and x0. We see that in each term. It starts with xn and it ends with x0. We can write that, this vector, we can write it x point to the power. Means if you remember in practical, I think 2, yeah, practical 2. Practical 1 and 2 are dedicated to matrices. And in practical 2, we have seen element-wise operation. This is element-wise. Means we apply the power to each element. But here, we have only one element, x. However, the exponent is a vector. The exponent is n. It starts from n and it decreases by a step of -1 till 0. So we apply the power. We apply the power to n, x power n, then x power n -1, and so on, till 0. Exactly that. Are the same. You use the element-wise power. Point here. Careful, point. And the second vector is the y's. Y starts with y0, then it increases y1, y2, etc. till yn -1, and it ends with yn. So always the degree is n plus 0 is n -1 plus 1 is n -2 plus 2 is n, and so on. So here it decreases, but for y it increases. So this is the second vector. Our goal here is to vectorize the sum, the formula of the binomials. And we can write that in Matlab, y to the power element-wise of 0 till n. This is a sequence starting from 0 till n. And the step is 1, the default. Okay. And now for the coefficients of the binomial, we have said that there are from Elkarkhi's triangle. So there are a third vector. Let's write it here, third vector. Third vector is the contents of the last cell, n plus 1, of Elkarkhi's triangle, the last row, which is equivalent to 1, n, and the last term also because of symmetry, n1. So the rest, the inner elements, we calculate them from the algorithm, of course. We have to call first the function genElkarkhiTriangle to calculate the coefficients, and then we apply the binomial theorem. How we do that? We multiply x and y by the coefficient, and we sum. This is the sum. Our sum is ti x to the power of n minus I yi from I to 0 till n. We can write that by the sum of the Elkarkhi's triangle, which give us the last row of Elkarkhi's triangle, un plus 1, which gives us the ti's, multiplied element-wise by x to the power of n, the first vector we have seen here. And then multiplication element-wise by y to the power of 0 till n. So this is the first vector. This is the second vector. And this is the third vector. We multiply element-wise. This element multiplied by this element multiplied by 1. So we multiplied element-wise, and then x and y with n, and so on. And once we finish multiplication, we get a vector of n plus 1 terms. We add all the terms in the vector using the function sum. And this will give us x plus y to the power of n. So instead of using a loop, it is better to use vectorization because it's faster, as I explained in the previous practicals. So let us now go to this is called the vectorized form, the vectorized form of the binomial theorem. When you use Matlab. In C or C++, you just use the loop for. It's much easier, simpler. But it is always advised in Matlab, if it is not complicated way, if it is simple, easy to vectorize it. Otherwise, better keep the loop form. So the vectorized form of the binomial theorem, as we can see, it's very simple. Let's go to the computer setting and implement this. So let us apply what we have studied on the notebook. This is the script. I called it binomials. TAR Scholar, Programming with Matlab, Practical 7, Algorithms. Calculate a binomial of a given order using Elkarkhi's triangle. By Tahar Jouad, the date 23 November 2023, Algeria. As usual, we clear the memory and the console, and then I ask the user to introduce the x and y and the degree. We get x and y from the vector, and we call Elkarkhi's triangle to generate Elkarkhi's triangle. We have already seen the function. It takes as input n, and it returns a cell array of n plus 1 elements. Each element is a row. Then we calculate the binomial using, in one single line, as you can see, using the vectorized form of the binomial theorem. So we have the last row, then element-wise multiplication by x to the power of n till 0, decreasing till 0, and then element-wise multiplication with y to the power of 0 till n. So all the vectors have n plus 1 elements, and we get a vector of n plus 1 elements. We calculate the sum of its elements using the function sum, and that's it, and we store it in A, and then we print it. So it's very simple, very easy. We just run it and see how it works. So as an example, use a vector, because you cannot introduce 2 or 3 or more elements with the input. So that's why I use a vector. So I use the same example in the series. So 1 and 0, 5. And I close the bracket, enter, and the degree 4. The same example in the series. And I get 5.06 to 5. I can do that also directly, 1.5 to the power of 4. The same result. Here it is a real number to the power of 4. And here it is a binomial, the formula of binomial. We get the same result, of course. So it proves that it works. Let us now come back to the notebook to improve the algorithm. We have seen the first algorithm. We have seen here genElkarkhiTriangle. The first version, we can improve that. We can make it twice faster using the symmetry. If you remember, when we tested the Elkarkhi triangle, we get, let's try it again. 15, for example. Let's show the figure here. You can observe the symmetry here. We can use that to improve the algorithm. We do not have to calculate the other half. We calculate only the first half of the triangle. The other half can be deduced by symmetry. This is the last row, but each row has this symmetry. So, as I explained it before, there is a symmetry in Elkarkhi's triangle. Therefore, we do not have to calculate the integers in the second half of each row, but we rather copy them from the calculated ones in the first half. So let us, because there are two cases, let us consider, for example, row number 6. The first case, the length of the row is an even integer. That is, the index is an even integer because the length of the row is equal to the index. So I equals 6. We are at the sixth row. It has 6 elements. And the second case is an odd length. So I equals 7. We do that to define the half. What is the half of a row? Because the half depends if it is an even and how to copy them. It depends on the case if it's an even length or an odd length. We know that it is equal to 1. The first element of each row and the last element are always equals to 1. And we calculate the first half. This is the half. The first half, as usual, using the same algorithm from the previous row, we calculate them using addition. Very simple. But the second half, these elements here are copied, are not calculated, are copied. This one is copied here, and this one is copied here. So we need to refer this element, the index of this element, by JE. JE represents the end of the first half. So JE is the end of the first half of the first half. So the elements that have been calculated. But here, it's a little bit different. So these elements will be copied, but this one will not be copied. It will be calculated, but it will not be copied. So the elements here will be calculated and copied, but the one here will not be. So JE will be JE will be here. So the first half to be calculated. First half to be calculated. But for the copy, we do not copy from JE, we copy from JE minus 1. So we copy that one here. Let's do also color. We copy that here. And this one here. Observe that we copy in the reverse order. we start from here and we go by step -1, while here we go by step +1. So this is the modification. And let's write it here. For the first half, so JE has the same meaning, but its value is different. So here JE is equal I/2, while here JE is equal, because it is an even integer, we use fix. For example, 7 divided by 2 is 3.5. So we use the function fix to get only the integer part. So I/2 plus 1. I/2 we get here 2, 3. 1, 2, 3 plus 1, we get 4. So the formula of JE, albeit it has the same meaning, but the formula is different. The second thing to note, what we copy from J equal JE in the reverse order with the step -1 till 2. And we copy 2. The elements are indexed from L, use an index L for the elements in the second half. So they are from JE plus 1 with the same step 1, with the default step 1 till I-1. Till I-1. And here J equal not JE, it starts with JE -1. JE -1. So it is also different with the same step -1 and till 2. While here L is the same formula. JE plus 1 till I-1. So we have the same formula for L here. And we have a formula for JE. And the index for the element to be copied we cross the first half using a step equal to -1 in the reverse order. So using this understanding, this information, we go to the computer setting, we modify our function to use this new algorithm. We do not calculate the element in the second half, but we copy them from the first half. We do calculate, of course, the elements in the first half, but then we copy them in the second half. And here the time complexity become actually the half, because we calculate only the half. In the order, time complexity becomes the order of n squared over 4, not over 2. So twice faster. Let's see that in the computer setting. So this is our second version of our function. This is the second version of our function, the same name, input and output. I just modified here the second version and the date, of course. And the first thing to do is to check whether n is an integer, positive integer. We set u to be a cell array of n plus 1 rows, and we use the flag even. Now this is new. What does this flag do? It checks whether the current row has an even length or it has an odd length. So I initialize it to be true, and then it will become false, because for I equal 1 it is false, and then I equal 2 it becomes true, and so on. It alternates false, true, false, true, false, true. according to the index I. We can, of course, use modulo, but we don't need that. So I use a flag, and I start it with, I initialize it with true. For I starting from 1 till the number of element of U, nothing new here, and we initialize the contents of the ith row using the function once, and then here we initialize JE, the end of the first half of the current row. First of all, we update the flag. The flag was true, it becomes false, because we use not. This operator means not. It negates the Boolean. If it is true, it becomes false. If it is false, it becomes true. So it was true, now it is false. So for I equal 1, it is false. It is not an even length, it is an odd length. For an odd length, we use this formula we have seen on the notebook. And for the even length, we just divide I by 2. And then we copy as usual. We use the previous row. In the cell UI minus 1, and the column J and J minus 1. And we loop from J till J, not till I minus 1, just the half. We calculate the elements in the first half only. And then by symmetry, we copy them. So again, we check where we start to copy using, if even is true, we start from JE. Otherwise, we start from JE minus 1, because the element at JE will not be copied when it is an even case. And then we copy the same formula for L, being even or odd. We use the same formula, JE plus 1 till I minus 1. The rest, the element in the second half. The rest of the elements that have not been calculated. We calculated only the element till JE. So from JE plus 1, we copy them using the index J. We copy what is indexed by J to what is copied by L in the same row UI. And then we decrement J, because as I have said, the element to be copied are indexed in the reverse order. We cross them in the reverse order. And the element in the second half in the normal order, in the forward order. So, and that's it. That's it. Very simple. The only here to be careful here is to use a flag. We could have used, of course, I even equal modulo I by 2, the remainder of division. If it is equal 0, then it is even. Otherwise, it is false. Then we do not have to do that. I even will alternate from false, true, and then false, true, and then false, true, depending of the loop, the index I. So we do not need to calculate the modulo. It's a necessary operation. That's why I initialize first. You have to initialize first to use this trick to alternate your flag. You have to initialize it first before to come into the loop. And that's it. Let's save it and test it. We use the same test. The test will not change. We have improved our function. All the programs, all the scripts that call our function will benefit from that. And this is the good thing about functions. When you modify your function, all the scripts using it, you do not have to change them. They will benefit from the gain in performance. So let's run it. And let's check 15. And as you can see, the same result. And in the figure, the symmetry, right? And in the textual, the same, 2, 3, 3, 4, 6, 4, 5, 10, 10, 5. Yeah, and that's it. Let's check also for the binomials. So let's try another example. For example, 7.5 and 3.8 to the power of 7. So we get a huge number, as you can see here. Let's do that directly. 7.5 plus 3.8. It's 1130. So 11, 3 to the power of 7. We get the same number to the power of 7. Let's display it. With 5 numbers after in the fractional part. We get the same as here. Exactly the same. And that's it for our practical. Let's make a conclusion and finish the practical. So to conclude this series, let us observe that for an algorithm, you must first carefully study the problem and the method, then consider edge cases, if any, and make sure you understand also the complexity time. I mean the time complexity, the performance, or how many iterations, the total number of iterations your algorithm is doing, and the cost per each iteration. The algorithms we have seen here in this last practical, the cost per iteration is very low. What is important is the number of iterations. But in the general case, you must also check the cost of each iteration. Like we have did actually in, I can't remember the lecture, I think lecture 3 or 4, when we studied Abu Kamil's method. So in Abu Kamil's method, the cost per iteration is expensive. Try also to understand the memory you are using. If there are any unnecessary vector or matrix, try to avoid, try to minimize the use of your memory. And finally, always write a script to test your algorithm. An algorithm that has not been tested and does not take into account the edge cases is useless. It will contain bugs and it will not be useful in practice. So we have said that this is last practical. We have actually skipped 2 points: graphical utilities in 2 and 3 dimension, and how to store data in a file, in a textual format or in a binary format. Because that would be too much for this appendix. However, we don't need that actually in the first chapters. When we need them, I come back. I think in chapter 4 or chapter 6, when we deal with data, interpolation and curve fitting, we need to store data in a file. We need actually, because that data comes generally from an experiment or from simulation, computational simulation. So it has to be, it has been done by another program or by another user. So it has been to be stored in a file. So in that case, I will come back to this appendix and add maybe 2 or 3 practicals to tackle these 2 points. They are important, but not important now. Now we have, I think, a very good view of a very good introduction of Matlab. So see you inshallah next time. We come back to chapter 1 with practical number 1. Peace.